All right, today we're going to talk about the instrumentation amp, which is an extension of the op amps that we talked last time, and we'll talk about what it is, why we use it, how to use it in a moment. Again, this is in the book. This is section 8.2.3. Before I get into instrumentation amp, I'd like to review the op amp lecture from last time. So this is a review from the previous lecture. We saw that we used op amps to create a linear circuit. So what does it mean to be a linear circuit? What's that mean? If I say this circuit is linear, what does that mean? So for instance, is a NOT gate linear? Is the output a linear function of the input? A NOT gate.
Yes.
No, a NOT gate? 0 to 1, 1 to 0? A half doesn't go to a half. There is no half. It's discrete. Digital stuff is discrete. But in analog stuff, we talk about the output as being a linear function of the input, y equals mx plus b. Okay? So that's what I say when we use the op amp in a linear function. Okay, we will have an expression that's linear. It turns out m and b might be a function of frequency. Okay, they might be a function of frequency. When we get to the filters, we're gonna let the gain be frequency dependent. But it's still a linear function. The output is linearly related to the input. Okay, so law of superposition, multiple sources. I can do all that stuff with a linear circuit. And the reason why we need op amps is to map the transducer voltage into the A to D range. Okay, so as you know, the A to D range is 0 to 3 volts. And sometimes we have a transducer which is not 0 to 3 volts, so we have to map it, okay, with a linear function. That's why we need the op amp in this class. And we had 5 design rules. Okay, and I'm going to repeat them on the next slide. But the other review from last time are these 6 things that are related to the use of op amps to create linear functions. The first of which is we used a linear equation to relate the output as a function of input. Okay? Again, it might have some s's or f's in it, but it's still a linear function. Okay? It's not discrete, it's not discontinuous, it's linear. Okay? We were interested in input impedance, output impedance, offset voltage, frequency response, and noise. Okay. So the definition of input impedance is if I have an input voltage to my input, okay, I'm interested in the input current. Sometimes this other terminal is ground, and sometimes this other terminal is another signal, and this is a differential amplifier. Okay? So, but again, we have input impedance is defined to be the input voltage over the input current. Okay? All right. Why is it important, by the way? Let me do the output impedance, then I'll talk about why it's important. Okay? The output impedance of a module, of an analog circuit, of a transducer, whatever, is the ideal output with a series resistor. So there's my output as seen by the oscilloscope, as seen by the other module. Okay. And any voltage drop across the output impedance represents an error. Okay? And how this is important is typically we will connect the we'll connect the module B input to the output of module A. And so what was the guiding force to input and output impedances that we saw last time? There was a guiding equation. It's going to show up on the test. It'll show up in life. When I connect an analog module to another analog module and I hook it up, I have to think about impedance. Okay? Because where's the error in this system? Where's the error? across Z out. So this represents an error. Okay? So in general, what we'd like to do is to map all of our errors to be less than the resolution of the A to C. Okay? And if I've mapped the full scale range of V out to 3.3, if the system maps everything to the full range, we can see this, and again, this error is a very simple equation, right? You see it? Error is equal to what? Right? V true times Z out over Z out plus Z in. That's Ohm's law. Okay? But since the output impedance is usually much smaller than the input impedance, we can approximate it this way. And so I can look at the ratio of Z in over Z out. Okay? Is equal to the error, to move error, okay, upside down V true over the error, okay, approximately. And I want this to be less than the resolution, so I'm going to make this bigger, right? So if the error is less than the resolution, then this is bigger than the precision. Okay, not greater than, not much greater than, just greater than. Okay, so that's where that came from. That's why it's important. All right. All right. The offset voltage, okay? Remember what that was? If we have the actual op amp like this, and we think of a ideal op amp inside, okay, then the offset voltage is the voltage at the input. So if this input here is equal to the offset voltage, then the output is going to be 0. Okay, that's the definition. And the consequence of the consequence of offset voltage is the error that we're going to get due to the offset voltage. The error at the output, well, the input error is exactly equal to the offset voltage, but the output error is going to be equal to the offset voltage times the gain of this circuit. Okay? So this will matter if I have a large gain and a large offset voltage. Okay? And we saw how to remove offset voltage last time. I got it, don't like it, number's too big. Or in other words, yeah, this, is greater than 3.3 over 4096. It's too big. What do I do? If this is bigger than that, I have to do something. What do? I buy a better op amp. Okay? For this, I buy a better device. All right. We talked about frequency response. And so now we're going to have a system, okay, with an op amp in it. And the gain versus frequency of this system typically looks like this. And there will be a cutoff frequency, and it turns out that this cutoff frequency, it's called the bandwidth, okay, times the gain is going to be a constant. And that constant is a function of that op amp. So we saw for the OPA 2350, this constant was 38 megahertz.
Dr. Barman?
Yep.
So is that gain G, is that, say, for any frequency or, say...
No, the gain is the gain of the amplifier. So for instance, okay, the circuit that we created had a gain of 100, okay, which means that this circuit is going to have a frequency response of 380 kilohertz. So it's the gain of the circuit at DC. Is that a better answer? This is the gain I'm talking about there, that.
So it's the gain at DC.
The gain at DC times the bandwidth is equal to a constant. And that constant is a function of the op amp. And again, if you want more, buy a better op amp. Is noise. And we're going to look at noise in the same way we looked at offset voltage, by the way. Okay? If we look at a noise of an op amp, okay, the voltage noise looks like this. In other words, it's noise that's added to the input before we get to an ideal op amp. So this is the real op amp here, and this is an ideal one. And the consequence of this noise is just like the offset voltage. And that is the op amp noise times the gain of this circuit is going to generate the noise at the output. Okay? And now what I'm going to do is I'm going to, as a design rule, I'm going to take the offset, I'm going to take the noise of my op amp and multiply it times all the gain to the ADC, all the gain from that spot all the way to the ADC, and that has to be less than the resolution of the ADC. In other words, 3.3 volts divided by 4,096. Okay? And if I want more lower noise, I'm going to just buy a better op amp. Let me do one more thing before we get to instrumentation amps. And now I'm actually going to do an exam question. This came a couple of years ago, exam 2. Yours is going to look just like this, but different numbers. Okay? I'm going to solve the problem as to why this was important. Remember the first reason for having a linear op amp, right? And that was to map the inputs from the transducer to the A to D converter. Okay? So what I'm going to do is I'm going to start with a problem that says it goes from 20 millivolts, minus 20 millivolts to plus 20 millivolts. My A to D converter is 0 to 4. That just makes the math easier without the calculator. Okay? Okay, so again, the problem is it's single-ended, and it goes from minus 20 millivolts to plus 20 millivolts. Okay, and I want to go to an output of what? It's my A to D converter, right? So in lab it's 0 to 3.3, but on the exam I want to go from there to 4 volts. Okay, you see that? And I want it to linearly relate. You see that? Vn minus 20 to plus 20 millivolts to V out 0 to 4 volts. That's what I mean by a linear equation. If it's less than 20 millivolts, I don't care. If it's greater than 20 millivolts, I don't care. I want to do that mapping. See that? It turns out the rail-to-rail op amp is going to save us if it actually gets bigger, but we'll get to that in a second. So I may just give it to you this way, in which case the first step would be to write this as an equation. V out equals 100. I can look at the total gain, right? I'm going from the difference here is 40 millivolts to 4 volts. Okay, see that? And then I need an offset, right? Because I can't take minus 2 volts, so I'm going to have to add 2 volts. Okay. So for instance, what do I get if the input is minus 20 millivolts? What am I going to get? 0. See that? Right? 100 times 0.02 is 2, minus 2, 2 plus, minus 2 plus 2 plus, I'm going to get. Okay. What if V input is plus 20 millivolts? is going to go to 4. Now I'm going to double check that. Now in this particular question, I actually gave you the equation, but nevertheless, I'm setting up why we want this problem. Okay? Are you with me? All right. So let's do it. Okay, so I'm going to erase this. Clear? Okay, I'll rewrite the equation. So first step was to choose a reference. And so you got to build it with a 4041. So in order to finish the test, what reference would you like to choose? Yeah, let's just pick a 2-volt reference. Yeah, why not? You could pick a 1-volt reference and it'd be just as easy, but 2 volts is pretty straightforward. So we're going to have this equation here. V out equals V1 plus V reference. Okay. The next step is to add a ground gain. Remember, ground is equal to 0 volts. That's a definition of ground. And I'm going to produce a ground gain here. I'm going to choose an M such that 100 plus 1 plus M is equal to plus 1. Okay? That's the definition. This has a definition. I got to make M to make that happen. That's how all the magic happens. That's a magic step.
Dr. Valman, what is this equation, Dr. Valman? Say 100 plus 1
Okay,
plus
I'm adding the gains. I'm going to sum the gains of all of the terms. Okay? I can have more inputs. Well, however many inputs I have a V2, a V3, a V4. I'm going to add up all the integer gains, all the gains of each of those stages. Okay? And if I make it equal to 1, it's going to balance the op amp, by the way. That's how this is going to work. It balances that op amp. So what should M be? Minus 100, right? So M is equal to minus 100. Okay? So we got V out equals 100 V1 plus V reference minus 100 VG. It's the same equation. Still works, right? Still maps minus 20 millivolts into 0 and plus 20 millivolts into 4. Okay? Still solves my problem. Now I need a common multiple of 1 and 100. 100, right? I'm looking for a common multiple. And now we go to rule number 5, which is choose resistors from 1K to a megohm. And so what ratio of resistors gives me a ratio of 100 that fits in that range? Right? If I need I need 100, a ratio of 100, what number should I choose? Yeah, I need 2 resistors that give me a ratio of 100.
100K, 1K.
Yeah, 1K and 100K. Right. What else could I have chosen? Still satisfied rule number 5. 2K and 200K, 3K and 300K, 10K and a megohm, right? And that's it. Because can't go over a megohm, can't go under a K. Rule number 5. Right? So I don't care. I don't care. I don't care. Okay? And those are obviously going to be easiest. The reason why I leave this up is it allows us to revisit the rules, right? The rules, the op amp rules. And what was rule number 1? Linear op amps always have rule number 1, and that is negative feedback. Okay? And so that's where the big resistor goes. Okay? Right, I'll use negative feedback. That's what makes it sing. Okay? And then what were the other rules are that the voltages at the 2 terminals are equal. Okay? And the way I'm going to build this is I'm going to make the ratio of these two resistors match the gain of that input. And I'm going to put it on the plus terminal because that's a plus 100. So you see the ratio of the feedback resistor to the input resistor is a ratio of 100. Okay. See that? The next one is a V reference. What gain do I want for it? 1. And is it positive or negative? It's positive, so I'm going to put it there. And again, the ratio of the resistor on V reference to the feedback resistor is a ratio of 1, so that I can have a gain of 1 right there. I got one more, and I got ground. Ground is ground, but it goes here because it's got a negative 100. And again, I want a ratio of 1 to 100, so there's my 1K. And if it turns out, if you go to the other op-amp rules, and we say Vy and Vx, if we make Vy equal to Vx, and you then use Ohm's law, you're going to get this equation. But it only works if the sum of the gains, the sum of the gains in each of the stages goes to 1. That's the only way this works. Let me do one more, just so you can see it. This, you've seen this one before. Okay, what's that called? This is the differential amplifier. And this is nice because it'll be an introduction to today's lecture. It's a differential amplifier. Okay, stage 1. Step 1. What reference do I choose? I don't need one, right? There's no constant there. I don't need a reference. Okay, step 2. Okay, now step 2. What ground gauge do I choose? I want the sum of all the gains to be exactly equal to 1. So what ground gain, how much do I need?
0.
Not 0, because then it will sum to 0.
Oh, 1.
Yeah, it needs to be 1. Okay. Again, I didn't change the equation. Right? You see that? I didn't change the equation. It's still the same equation. And so now I need a resistor, okay, with a ratio of 10 now. Right? And 1. Common multiple of those. 10K and 100K. Yeah, I need the ratios that fit. Okay? So now I'm going to build it. V1, Rule number 1, don't forget that. Okay? Okay, so the gain for V1 is going to be 10. So what resistor value goes there? 10K. All right. What about V2? It's negative, right? You see that? Negative. And it needs a ratio of 10. But got one more, right? VG. And it's positive. Right? So it goes into the positive side. And just to make it look exactly like the circuit that I drew earlier. But what value goes there? 100. Does that look familiar? That's the standard differential filter, differential amplifier we had before. We don't ever use this one because it's really crappy. It has bad input impedance. Because if I put a volt at V1, I'm going to get a fair amount of current. because it's going to go through those two. Remember, it's the input impedance is not in tera ohms or gig ohms; it's in kilo ohms, right? The input impedance of this is going to be 110 kilo ohms, and that's not very good. So that's bad. There's another one that this is not very good at either. Okay, so with a differential amplifier, V out equals some gain times V1 minus V2. Okay, we're going to call this the differential gain. And whenever we build one, we also get what's called the common mode gain, just because it happens. And the average of the two is that. And so whenever we actually build an amplifier, we actually get some common mode gain. And typically, the common mode signal is noise. For instance, in your electric microphone, in sound, what's the average voltage mean? Doesn't mean, it's not signal. It's crap. We want to get rid of it. And typically, the differential mode is the signal. Okay? And if you ever heard the term signal to noise ratio, okay, it's important. And that is going to be a function of the differential gain over the common mode gain. And the circuit we just did has a really crappy common mode rejection ratio. Oh yeah, and this is defined to be the common mode rejection ratio. Okay? Often it's written in decibels, right? Often it's written in decibels. So we would define it this way: common mode rejection. Is it a 20 or a 10?
20.
It's a 20 because that's voltage gain, right? These are voltage gains. 20 log 10 of the differential gain over the common mode gain. All right. So when we see the common mode rejection ratio of a differential amplifier, that's how it's defined. And it's important because it's the thing that's going to reject the noise. Right? With me so far? Okay. So now I'm motivated why we hate regular op amps, and we want to get out the big guns. This is Texas. Everything's bigger in Texas. Okay? If you want to go fast, you want a fast car, you don't go to the junk dealer and soup up an old car. You want to go fast, where do you go? You go to the BMW, the Audi. You go to the Jaguar dealership. Chevy, Corvette. You're getting yourself, Formula One, faster and faster and faster. You go spend some money and get more. This is really important. Common mode rejection ratio, signal to noise ratio, gain, all these things are really important. And the manufacturers out there are building you faster and faster cars. We're going to get faster and faster ways to create a differential gain. Okay? And it's called an instrumentation amp. And there's thousands of them out there. We're going to give you one today for Lab 9. But suffice it to say, we must have a differential signal that we wish to amplify in order to use an instrumentation amp. So an electret, for instance, it doesn't have an instrumentation amp in it because it's a single voltage. So whenever we encode the information as a difference in voltage, whether that's V1 minus V2 or V2 minus V1, that is going to be a necessary, it must be true in order for us to attempt to use an instrumentation amp. Okay? And then we need one sufficient condition. Okay? So we have one necessary condition and then multiple, one or more of which must be true in order for us to try to, or to require to use this expensive chip. Okay, so this is an expensive chip. We got a bunch of them. You can have one. If you need differential and large gain, this is your friend. If you need differential and large input impedance, this is your friend. If you need differential and common mode rejection ratio, this is your friend. And that common mode rejection ratio usually embodies itself in the term low noise. Okay? Or two of them, or all three of them. So we'll see some examples of use of the instrumentation amp that satisfy one, two, or three of these conditions. Okay? But in order to use this expensive chip, please don't hook it up to a single voltage and ground the other pin. Okay? You get a lot of points off in the test if you tell me that. And don't tell me it works. I'm going to go right back to you and say, you just wasted $6. You could have solved it with rather than use a $7 chip, you could have done it with a $1 chip. Use it with an op amp. Okay? So don't violate rule number necessary condition. All right, so it's fairly straightforward. You just buy it. You know, it's like you want to go fast. You go to the Jaguar dealer and you give them some money. They give you the keys and zoom, you're going fast. That's why people buy their BMWs in Germany, by the way. You ever heard that? You know anybody who owns a BMW? Yeah, they go to Germany to buy it and ship it to the United States. They don't go up North Austin and buy it. So they go on the Autobahn. Yeah, just once. They like to go fast. That's why people buy those cars. Go to Germany, buy a fast car, drive it on Autobahn, ship it to the United States. Okay. So, yeah, but they don't know how it works. Okay. It turns out it's not too bad if you actually want to know how it works, because this is university.
Dr. Wagner,
Yeah,
this
go.
large gain is a differential gain, right?
Yeah, large differential gain. Yeah, absolutely. Okay, large differential gain. Yes, absolutely. Yes. You want a small common mode gain. That's why it works. Okay. And it actually is this circuit. And I'm not going to derive it for you, but if you can imagine, it's not that complicated. Because we're almost done. Plus, minus. V2 V out equals gain times V2. That's basically how it goes. And it turns out this resistor here is the resistor we're going to see externally. And so it has a great common mode rejection ratio. And again, I don't want you building this. That's like buying a Ferrari from a kit. Okay? That's like buying a computer from a kit. You don't buy a computer from a kit. You buy a computer from Dell. Okay? Or HP or Apple. I don't care. But you don't build this. But this is how it works. It has a great, it's good common mode rejection ratio. You can see what the input impedance is. How much current is flowing into here? None. That's why it's got good input impedance, right? All of these resistors are completely balanced, so it's got good common mode rejection ratio. All right. All right. But the one we're giving you has one resistor that shows up here between pins 1 and 8. And that resistor will affect the gain of this. So if you leave the resistor off, remove totally, it's got infinite, you'll see you'll have a gain of 5. If you put in a resistor of 200K, you'll see that it'll have a gain of 6. If you put in 100K, it'll have a gain of 7, that kind of thing. Okay, so you can adjust the gain of this by choosing that resistor. It also has an offset if you want, and it will. In some of the circuits, we'll use it. In Lab 9, we're going to ground it. Okay, so, but it does have a large input impedance.
Dr. Wagner,
Yeah, go.
is the resistor that you just rounded on the diagram you drew, is that resistance between 1 and 8 pin?
Yes, yes. Between pins 1 and 8, we'll put a resistor, and that resistor will determine the gain of this system. Okay. In Lab 9, the gain's going to be somewhere between 5 and 10. That's what we're going to need. But we are going to need a high input impedance and good common mode rejection. And it is differential. Okay. Here's a review from way back in Lab 5. I don't know if you remember how this thing works, but it's time to know how it works. Basically, there's a constant voltage across here. Okay. That's due to the diode-ish, the diode nature of this device. And so that's the VD. This is a constant. So if it's operating within specs, you'll see a voltage difference across R1 of 1.233. That's how it works. And that means it's very accurate, very stable, low noise, low temperature coefficient, that voltage. And now what we're going to do is choose R1 and R2. Since we know the voltage across R1, we now know, and we know R1, and we put it down there. Now we know the current through R1. Okay? And since we know the current through R1, we can now figure out the voltage across R2, okay, such that the voltage across R1 plus the voltage across R2 is whatever voltage we want to have on Vref, regardless of this voltage and regardless of that current. Okay? So the voltage V reference is going to be independent of I reference and independent of the supply, because this is a constant, and R1 and R2 are resistors that are constants. So therefore Vref is a constant within some bounds. Okay? And that has to do with the maximum current. There is about 80 microamps going through there. You can calculate how much current is going through here, right? That's this, I2. And so this whole thing, these two together, we're going to call IZ. And then what I got to do is choose a resistor RS such that 3.3, this current here, is obviously equal to IZ plus I reference. So we're going to choose a resistor RS to set the maximum current associated with the reference. And if we choose a resistor too small, in other words, if we have too much maximum current, it's just going to get wasted. Okay? It's going to get wasted. It's going to waste itself through here because it has to. If we choose it too small, then your reference voltage will drop because there won't be enough current to drive this system. So that's how we and this is important when you solder your thing down in lab 11 or use it in lab 9. If my guess is this resistor ought to be somewhere between 1K to 10K. If it's much less than 1K, you might be doing something wrong. If it's much greater than 10K, I'm sure you're doing something wrong. Because 10K is not even enough to drive the ship itself. Okay? So watch out for this resistor. These two are fairly easy to get because those show up in the equation for the reference. But the third one's a little bit tricky sometimes. All right. Questions on that? Okay. All right, so now I'd like to show you a couple of examples of instrumentation amps. This is an electrocardiogram. It needs large gain and common mode rejection ratio. Okay? Because you put the electrodes on your skin, you got a gain of 2500, and common mode is 60 hertz, by the way. Common mode doesn't always show up as common mode on this signal. It's going to show up as a 60 hertz, 20 kilohertz, whatever. A electromagnetic field pickup will generate common mode. Okay? And so here's my gain. It's probably best to make this about 10 and make this about 200. This, we've seen that before. You seen that? What's a resistor in series with a capacitor, and the capacitor is on my input? What's that? We saw that in the electret. Capacitor at DC does what? It's an open. Okay, that's a high-pass filter. This is a high-pass filter right here. And the high-pass filter is 1 over 2 pi RC, where 3.3 microfarad times a mega. This is an amplifier. Okay, it's a unipolar amplifier, but it's one of the ones we did prior. Okay? And then this is a low-pass filter. We're going to do that in the next lecture. Okay? This is lab 9. I'm going to come back to this when we get closer to lab 9, but basically we have a bridge, and the bridge is the output of the bridge is essentially a differential voltage. And so we're going to use an instrumentation amp in place in lab 9 because we have a differential signal coming off the bridge. Okay? This is my transducer here, and the other 3 resistors are constants. And that generates a differential voltage that I want to amplify. Okay? And I want to have a large input impedance. Okay? So that is the reason to use an instrumentation amp here. We saw thermocouples a couple of lectures ago. We'll use a thermocouple amplifier for 2 reasons. First of all, the necessary condition, it is differential, and the 2 sufficient conditions, we want a large input impedance and a large gain. And we'll talk about the low-pass filter next time. So in summary, instrumentation amplifiers are like the Jaguars of op-amps. Okay? You use them when you need them. And when you need them, it must be differential. Okay? Like a bridge, like a biopotential, like a thermocouple. And it has to have one of these sufficient conditions. A large gain, that means over 100 maybe. Okay? Over 100. Great input impedance. So 110 kiloohms is not good enough. Or a good common mode rejection ratio. And the other way you can tell you need good common mode rejection ratio is when the term is low noise. All right, next time we're going to do filters, questions.